Greetings, gentle readers, fellow earthlings. Today is February 25, 2026, with reading foundations today from a study with Ross Finlayson. Here's some more just going through a box of books, a bit of my library, relating that to the concepts of the canon and the dogma and the doctrine, which arrive at our modern, as they may be, accounts of reason and theory. The Theatheory being putatively candidate foundations, the theory of everything, at least true, the theory. Theatheory, where in an arguable sense, truth is the only quantity in the theory. And as for matters of contingency and in theory, then it's true that there can be abstraction and conjecture and all sorts of the picking up and the putting down the theories without necessarily the ontological status after a given ontological commitment, sort of ontological activity with regards to the teleology, the purpose or the being or the truth of the things. That this is just a usual sort of Platonistic account, as well advised by the rationality. So that when we look to the historical accounts, like of the Renaissance of idealism, or the Enlightenment of analyticity, or the analytical tradition, for idealism and the analytical tradition, both make for each other a quite thorough and wide account of how there can be one true theory, then that every individual has their own perspective on truth objectively as the inter-subjective. So the inter-subjective is the usual criterion given to that something that can be related has to be able to be relayed to be communicated in a sense for the intersubjective. And then that's for matters of, as Kant helped define, for phenomenology and the phenomena of the noumenon and the noumena, the mental senses, that for thinking and feeling beings, that it's sort of a lower common denominator to have the physical senses. And it's always then for an account of thinking beings, the mental senses. Here, an object sense corresponding to matters of perception and the interpretation and recognition of utterances or symbols or these sorts of ideas, thoughts, concepts. That then the account for that being a place for the presence of a unified sort of account, a holistic dual monism, accommodating that the void and universal turn each other over in this Entbergung, the showing and the hiding of the knackabout, the turning over of the items. That this sort of, again, paleoclassical and postmodern account intends to be a very classical and modern account. And then for the super standard and the extraordinary and these sorts of things. Grandiose, ambitious, correct, one hopes. Let's see, there's some books then. This I've read quite a while ago, and this is the paperback edition of what was in the hardback edition is quite a large tome, Salt, A World History. It basically describes the notion of salt as an commodity, and then also with regards to its necessity among commodities. The commodity usually intends to relate that something is just a material that is of an aggregate sort, and for matters of grade and the like, or quality, that it's mostly just about the quantity. And so salt then, and then for matters of supply and demand and scarcity, then similarly for like the story of oil or something like that, this book and that book about the story of oil or history of oil help to show that there's kind of a great account of these kinds of matters of resources and the strategic and the resources and these kinds of things. So this is good reading, and I'm not going to get into it here, but it does have quite a bit of discussion about all of the ancient trails and the development of commerce and the commerce across large and long distances. For example, the Sahara, and the notions of that in some places these commodities are readily available, abundant, and even almost valueless. In other places, they're dear and prized. And then with regards to the great role of salt in the preservation of food was the other usual sort of notion, or as for a barrel full of herring, say, the salted herring. That this book is pretty good, and I won't get into much more about it here, but it does remind me about that history of oil with regards to products like petrochemicals that once were just like abundant and even like the price was zero or negative when water was more dear. And with regards to a gallon of water or a gallon of oil or a gallon of milk, that they have this interplay of the flow of them through the economy and with regards to their function and their purpose and as the needful of the things. Recently enough, and for quite some years, it's been well known that gasoline or sustainable aviation fuel, given electricity, can dissociate the chemical bonds of carbon dioxide to make carbon monoxide, basically. And then similarly electrolyze water, separate hydrogen and oxygen. And then to follow as for something like Fisher-Tropsch, a chemical process involved in the polymerization of these sorts of compounds, which is well known since at least World War II, when it made it possible to make liquid fuel from coal or otherwise the tar sands or shale, these sorts of things. Fisher-Tropsch. Make it so that these days they do have commercial products that make sustainable aviation fuel, given electricity, which can be liberated in a sense from any of a number of renewable forms, to make the usual most common source of fuel for the fleet of vehicles that are liquid fueled. With petrochemicals and hydrocarbons and gasoline mostly, with regards to gasoline and diesel and kerosene and other fractional distillates of oil in a usual account. That it's approaching a reasonable price with regards to that. Basically, a little gasoline machine can be put out in a field and using wind and solar basically make gasoline. So this sort of idea of an application of technology, and it's not super high technology, it's pretty well understood, and even to the point where it's commercialized and that it's even, how one would put it, economical, can really make for a great account of better living through these matters of physics and chemistry, just to go to show that for all we know, it's already quite in use with regards to the tar sands and stuff like that, or the sources of fuel and the scale of these things, that it would make for a great account of something where technology actually improves the fate and the lot of the common man. Then with regards to that being affected in relation by the notions of global warming and the sad reality of climate change and the disturbance of the environment and ecosystems by matters of global warming mostly, then has that it's a carbon neutral process, carbon in, hydrocarbons out. And so at least that makes for a greater sort of account of renewable and sustainable economies vis-a-vis the plainly the consumption or the consumer-based economies, which at some point are not efficient. All right, let's get into one of these next books here. I found this in a bookstore, and so I'm curious about it because it says infinity on the title. And infinity and continuity here are accounts of terms as describe matters of reality and mathematical reality that are greater than or include all what makes up the character of the continuous domains and the finite, the bounded, the unbounded, and the infinite. It is, for after Aristotle, the potential infinity, the actual infinity, which is also a part of Aristotle's works. That the infinite and continuous then get into the infinitely divisible and the discrete for the analog and discrete and these kinds of things. So for an account of mathematical infinity, oftentimes, besides the usual symbol everybody knows for the infinity, kind of like the lazy 8, or the 8 on its side, it looks like, in a sense. The lemniscate, which is also related to the ouroboros, or the circle in these sorts of accounts. The lemniscate for infinity, as a mathematical placeholder and marker, has that as a superlative. It's sort of for an example of where superlatives can exist for the language and in closed categories can be said to be well defined, but comparatives and superlatives for more open or infinite categories, or generally enough, that the application of superlatives is making for careful distinction between just saying things that can never possibly be true and by definition are just wrong, to have something instead about how we can talk about infinity that's the real mathematical number. Of course, every child knows infinity since they first hauled it out as winning any matter of ordering and relation as by the natural order of things and not just by a bizarre haphazard rule or a claim. That instead, infinity is great among numbers, and it's greater in its greatest. And the comparative and superlative kind of come around and go around. So that kind of idea then getting into how we can have a formal account of mathematical infinity and the infinitely divisible is for atoms, and the then iota values, iota being a small account, kind of the opposite of infinity, and iota, an infinitesimal, yet with somehow real analytical character, and that these infinities are scalar infinities and real valued, or they live on the projective real number line somewhere, real infinities, vis-a-vis the matters of the Gesammelt, the collection, German word, Gesammelt, meaning collected these things, the collections in infinite multiplicities, vis-a-vis inconsistent multiplicities, that then this book, it says clarifying infinity is the title, and it has a symbol for infinity. Wallace's lemniscate, it's usually given, by David Johnson. And from what I understand, it's kind of just self-published out of Troutdale or something like that, Oregon, 2025. And so it is the preface, and then part 2 is Zeno's paradoxes, and then the author, I haven't read this yet, but it just has some mentions of the classical expositions of the superclassical, or Zeno's not paradoxes, but setups and zatzas of what it would have to be resolved. And then with regards to points and lines, and then part 4 here is infinitesimals, and then part 5 is cosmological arguments with sections with regards to Aristotle's, the unmoved mover, John Philoponus, Kant's first antinomy, or antinomy is, not its own name, antinomy, so it's a paradox, but it's not a paradox here. Saadia, I haven't heard of before. Kalam, cosmological argument, William Lane Craig, Thomas Aquinas, and Avicenna. Part 6 is for the infinite universe, infinite duration, infinite extension. It's about the Big Bang Theory. Here it's covered, or at least often mentioned, that the Big Bang Theory and the steady state theory, they each fit the data, and neither of them are falsifiable. So either one kind of has its place in the things. Infinity and probability with regards to likelihood and chance, and here is about one of the considerations given to whether a million monkeys out of typewriters would result being Shakespeare. But essentially, in a large enough account after evolution, as Shakespeare was just a monkey, and whether or not he had a typewriter or a quill pen, and whether or not he was actually a panel of a man, and all his notes show up in Francis Bacon's Waste Book, being aside, there's issues with the probability theory about infinity and classical probabilities, and not just what makes for the usual central limit theorem, that there are mathematically multiple laws of large numbers about the independence of the model of arithmetic, as whether it's standard or non-standard, a generic extension or a generic fragment, that there can't really exist a standard model of integers at all because it would contain itself and thus be non-standard, or that it's merely partial or unbounded potential, so that the usual account of an ordinary affinity is at best merely always an ordinary fragment of a model of integers, the infinitely many integers, that basically defining the property of whether a model of integers is Archimedean or not, whether it has no infinitely grand members, yet it always has infinitely many. The accounts of models of integers since Archimedes, that for probability theory, then since there's three laws of large numbers and three continuous domains and three Cantor spaces, then there's three limit theorems, and then that besides the non-standard models of arithmetic and measure, the great account of numbers adding up, has that the how one might say probability theory is just so equipped with that automatically. And then for things like the error record and the long tail, besides things like the central limit theorem for in uniformizing and polar limit theorems with regards to a mode and modes, and usual statistics and summary statistics, that's sort of explored here. But really the point is that when you hear about non-standard probability theory, if, for example, you're interested in probability theory and the non-standard, and look to find non-standard probability theory, that it affects to reflect not only about Bayes' rule and when it doesn't hold, about chance and uncertainty, or the Bayesian, Jeffreys, and Knightian, and these sorts of counts, that it's also, besides sampling observer and measurement effects and matters of feedback in the systems, that there's plenty and a lot going on in such usual matters and accounts of the different integro and the integro differ in differential systems and what are integral systems, those adding up. That the author here mentions something about that. Different sizes of infinity, and then he refers to Al-Kindi and Al-Ghazali, Jorg Cantor, and Cantor's Paradise, Lost, is the section 8.3b. And in conclusion, Tristram Shandy's autobiography and Hilbert's Hotel. So Hilbert's Hotel is generally the account of Galileo's paradox. Galileo saying, hey, I can line up the numbers, and then I can line up the squares, and I can put the nth square next to the nth number. They're the same size. And that violating the notions of the integral moduli has this. So besides that, the standard model of integers doesn't exist, or it's only a particular contrivance is in the middle. It would have to be after the Pythagorean and Cantorian to be in the middle of that. Then there's the account for the integral moduli. So often you'll hear about a formalization of numbers, the integers, as after Peano, Giuseppe Peano, who besides accounts of integers also has counts of Peano's infinitesimals, which kind of match to the geometric series, and nobody talks about because they would bring real analytical character to these non-standard accounts. Yet I do, and it's remembered, Peano, for not just the account then that he's enshrined in all formalization of mathematics, is saying is like, there's a number that's the least, 0, and then there's a next, and then there's a next. and then for addition and multiplication, just basically kind of revised as after that. The numbers are not merely defined by the relations. Numbers are defined by all their relations. So the integral moduli is for the integral is as much or more so than for accounts of the density of numbers in the numbers, like the evens in the integers or the odds in the integers. The multiples of 3, for example, 1/3 of those being integers, according to any matter of asymptotic density. The Galileo's account is after the equivalency of countable and the countably infinite sets. Still has it so that after aliquot parts or Robert Gross test and these kinds of things, the medieval philosophers, hundreds of years before that, and since the Muslim Enlightenment and since the Greeks and all that, and the as part of the scholastics, one would aver, as after the Greeks, because they're Aristotelians. Then it is so that then getting into for Paul duBois-Reymond and then his infinitar calcul, that being in the 18th century, bringing that back together, and that for Newton and Leibniz both, it was infinitesimal analysis was what we call the real calculus or real analysis. That then I'll be interested in what he says about Al-Ghazali and Al-Kindi and Al-Ghazali about then with regards to Cantor. And Jörg Cantor's account is after the Geschammelt of sets and the set theory, the Mengen-Lehre, the set reading or set book, Mengen-Lehre, Mengen theory, set theory. That there are many accounts of these already. And then it's a great simplification of sorts to then arrive at this, like there's one actual infinity, Aleph 0, the cardinal of countably infinite sets, the least infinite cardinal, and whether that in various models relating that to integers, because it's not an integer, it's a cardinal. And cardinal is not even a set in set theory. It's an equivalence class of all the sets with the same cardinal. By all the relations, by existing all the functions there could be. So that said, a great simplification of the things or the matters, and it results just one way to say there's a strict inequality between cardinals, and a trichotomy, meaning they're either greater than, less than, or equals. So that sort of ordering relation being for another theory of one relation, as set theory is a theory of one relation, and not member, because that's kind of its inverse relation for classes and sets, their distinction. For ordinals and the matter of being defined by being lesser, say, than another, or greater, conversely, a theory of one relation, that the ways these are modeled in terms of each other is by all their relations. So getting back around then to Peano, Giuseppe Peano, and the idea was like, well, what's a model of integers? It's just like start counting. It's like, well, that's one way to look at it, but it's more, and that's then reduced and simplified to be like, well, it's just an inductive set now. That's enough. It's not enough, because it's all the relations of integers that make then for the integral domains from group theory and this and the like, the integral moduli. That everything about number theory is its own theory. Then that they're all, no matter how it's done, all equi-interpretable by these fundamental theories of relations, the Heino theories, one theory, many theories, yet really one theory, explicating and interpreting and defining each of these in terms of the other. That thus for this author, I haven't then read all this, and I'll be looking to find some particular interesting details, and what the author found is interesting and clarifying. This book is called Clarifying Infinity, about infinity, but not oversimplifying or eventually closing what's really the open, or making ordinary what's really the extraordinary. Newton and Leibniz, or Leibniz, I'll always pretty much say Leibniz and spell it with a T. Oh, Russell on empiricism. Here, there was a comment the other day I made about Quine and Russell and their empiricism, and perceived hypocrisy, because Quine, as after his levels of modal relativism, and then that kind of just setting up, there's like a few stories above Russell, and just isolation, restriction of comprehension, and significance is like, now there's nothing left but to stand on that. Has that then the empiricism is part of, after the analytical tradition, what kind of results when there isn't the mental faculties for the mathematical platonisms, objects, to exist, that the real continuity and a real infinity exists. Yet it makes for a formalization that's more easily relayable. Has that it's not that much more difficult to relay a greater overall thorough deductive account, which would necessarily entail that its readers and the users of this account would be able to defend all matters of reason in this account, and not just necessarily read it off. It's the notion that induction never fails is an only inductive account itself. And the riddle of induction basically gives that the quasi-modal account of Russell and also Quine, although they give then kind of formalisms of like, we're building numbers, they have the character, these that we call standard and Archimedean, have that the continuity and infinity have more and better, and again, all the relations that they have. It's expansion of comprehension, not restriction of comprehension. So academically, this author, David Johnson, makes a question about the Russell and about the theories. Pickover and Orzel is mentioning it, about the convergence series. Here we've been talking about like the infinite series and the big N and the little n, and double power series. And then also with regards to the account of the Maclaurin-Clairaut account, which kind of figures out a way to put Taylor and Fourier together, and when they have the terms as would be telescoping to be carried down, how that could be so in the infinite. The superclassical result of Fourier analysis, that's still a thing. And then as with regards to derivational or differentiated truncations that make for a Taylor series, that are, of course, the most commonly used, or among the most commonly used numerical methods to estimate something when its entire infinite series can't really be given a closed form expression. That these matters of after the development of Fourier analysis, as was read here from Gonzalez Velasco in his great book on Fourier analysis and boundary value problems, has that the development of Dirichlet after Fisher, and then for Heine, H-E-I-N-E, Heine, make for that. That's another sort of superclassical account, again, to have the double-reductio, to build a model of the composition of terms, an inner product, as from this one. Then there was also built this sort of an idea of a hat analysis, and it's like, well, instead of saying that all these different waves can add up to, finite smaller waves can add up to a richer, more detailed, more dense, wider wave. It's like, well, what about if it's just kind of a triangle, and then those, as they drop down, could also be used to essentially make it so that then infinitely many of those could stack up again, making for a sort of triple reductio. But another way to show that the superclassical accounts just keep building and provide real analytical character. Before getting into matters of the quasi-invariant measure theory and halving and doubling spaces, Zeno's included, and after Vitali mostly, the revitalization for measure theory of not a real functions. It's a function, it's not a real function, it's not real valued, either its inputs or outputs. Not a real function like the Dirac delta function, with real analytical character, like its area equals 1. Or here, the natural units equivalency function, which is central and primary in matters of defining continuous domains, particularly 0 to 1. I wouldn't imagine that would be available to the author. So this clarifying infinity appears to be sort of a historical account and a kind of a standard account. So the usual inductive impasses, or what would be possible to make arrive at contradictions of infinity. About the supertask, and like what it means is like, well, we can never get there because it's half and half and half and half again, and that's just smaller and smaller, but there's infinitely many of them. It's like, well, if that takes half and half and half time again, also, then that adds up back up, and it gives for the account of why the geometric series, or the usual account of the arrow, or the archer of Zeno, or that the infinite divisibility of time, according to doing it half and half and half and half again, when the only possible way to divide something is in half, has that it's just a pretty simple then deductive account that arrives. It's like, now the geometric series is our prototype of these things for an iota values, because basically those can be broken down ad infinitum to make this like standard infinitesimals, call them iota values. An infinity of them is equal to 1. That's most familiar to people who know differential analysis and differential calculus, because that's what the differential sort of is. It's not so as according to the formalization usually given by delta-epsilonics, the totally cool and perfect sort of inductive account, which gives for the field axioms, and after field axioms, the complete order fields account of real analytical character, the fundamental theorems of the calculus, the derivative and the integral, after the intermediate value theorem, upon which it is built, that these line reals also have 1. And so that's automatic then. It automatically equips mathematics forever with that among, again, all its relations. Points, particles. Do points have sides? Do points have ends? Do points point anywhere? You can point at them. You kind of have to say, well, take all the vectors in the space that point at a point. How many does it take? Given a perspective, given a slice. So the points, defining points can never happen without defining spaces. That's how axiomless geometry arises. Just like axiomless natural deduction is like, how about nothing? How about everything? They reflect each other. And points and spaces make it so then, well, it's just like a line connects them, or it's a spiral space-filling curve out through all the infinitely many dimensions of the space. Geometry, or theory on a platter, as it was put. Then Euclid's is just from identifying that by reductio, that's like, well, yeah, you know, we found the shortest distance, and we're going to call that a straight line. And so that any 2 points define one. So it gives Euclid's axioms for free. And then there's, with regards to the parallel postulate and the double angle postulate, which is not actually explicit in Euclid's geometry, the accounts, but kind of defines, you know, it's like, well, what is a line when it's an angle? These kinds of things. That's kind of also addressed here as to why foundations really does include this from just pondering the fundamental question of metaphysics. It's true, so it's natural and it's real, and that's kind of a great account. Might not have been available to this author, especially just trying to relay that, and then also as well as with what was relayed to him, or what is the sum of his influences. So what I'd be curious when I'm reading something about clarifying infinity, I'm looking for something non-standard and interesting. But not just what just avoids inductive impasses and what would be paradoxes that could be easily made. So if I'm not going to find that in this book, I don't think. But it does demonstrate a great facility with the usual ideas of classical constructions. For example, he mentions Galileo Galilei thought that a circle is a polygon with an infinite number of sides. This is a totally usual and great sort of idea. I mean, it's not finitely sided, but it has the isoparametric theorem, which all the regular polygons build to. that's around since antiquity from methods of exhaustion and all that kind of stuff. And so saying Galileo Galilei thought so, meaning that he claimed so and said that it was kind of like so, and then it's the real infinity of these sides, or it's about defining the points and these kinds of things. With regards to the isoparametric theorem, I kind of have that, a circle is what a circle does, and this kind of thing. And relating to that, the axiomless geometry, that's the usual kind of thing. Al-Ghazali, an Islamic theologian, wrote a work called The Incoherence of the Philosophers. And he gave a critique of Avicenna and Al-Farabi, as well as ancient Greek philosophy. So I imagine it's to make for find a paradox and then just make something out of it. This speaks to the account of ex falso quod libe. It's like, well, I'm showing you how to do a proof, and I'm showing you how to do a proof where if you make a wrong step, then following obvious natural derivations, you'll arrive at something wrong, and then you'll wonder what misstep was it that made it so. It's like, well, actually, it's not out of fallacy ex falso quod libe, whatever. It's ex falso out of fallacy nihilum, nothing. So what you got out of that was just like an image or an echo, a hollow shell of what isn't, held up by the sum of influences and the ideas of that the how one might say that the fallacy did it, because it's not that the fallacy did it, it's that the mistake did it. And so ex falso nihilum then makes for, it's like when we find a mistake, we strike it out and understand where it came from, instead of just saying, oh, it's not my fault, or something like that. So ex falso quod libe is, besides just being a way to shift blame and responsibility, and then also to say, it's like, well, it's just an obvious fact that by making a mistake, now you've made another one. Is not to be related to matters of actual truth and actual fact, the structure of all these things, because naturally enough, it's ex falso nihilum. So that way we don't have the quasi-modal aspects of logic which arrive at these things like ex falso quod libe, as after the classical account of the principle of non-contradiction called the law of excluded middle, or the principle of excluded middle. There's no third, it's just true or false, can't be both, a syllogism is so or it breaks. How's that? That's broken down about the principle of inverse instead of non-contradiction, and the principle of sufficient and thorough reason above the principle of sufficient reason. So to make for Occam's usual accounts is like, well, deduction is a great account of keeping things simple, and it's like, well, yeah, but not too simple, and about how simple things arise from being infinite completions in continuity. Has that they do, and they must, and so infinity is in the theory, and it's continuous in this way. So the author's mention of Galileo then was about geometry, and then about the number theory. That maybe he mentions it somewhere else. So then it gets into matters about the matters of truth and belief, and then relating that from making logical fallacies, and then using that to break open into saying, well, then it's supreme, and the omni is thusly bringing itself in, and that's a fallacy itself, because the supreme and the omni does not necessarily observe what people want, or that it intercedes on their demands. That's a wrong thing. So something like a cosmological argument for teleology and theology can exist on its own largely, without relating it to any earthly matters at all. But doing so is what's the word? Equivocation. It's a sophistry and the casuistry, in the negative appellations of those. Talks about Ghazali and Craig, cause. So cause here is causality and teleology, and that's inviolable. It's logical. It's natural. A question of empiricism. So that is why the audience laughed when Mark Twain quipped that quitting smoking was the easiest thing in the world. He knew because he had done it thousands of times. So that's a matter of like the empirical and fallacy. Well, it's the same, so that it's a great saying, and Mark Twain is known for a lot of great sayings because they're true. They help illustrate a truth, especially because his observation of it is not like, and that's the fact. He's like, and now you have to think about it and call me wrong. To make for yourself why that is not just an absurdity or a lie. You got to turn it over and see why it either way it's what it is. So Aristotle won't be made a fool, and furthermore, there's some other account of not and Hegel. And Hegel will work it out. But I had a good quote the other day about Hegel. Maybe I'll recall it someday. About Aquinas and the merely possible. Just as it would be a self-contradiction to say that a square circle does exist, so the antinomy makes for then squaring the circle or circle squares, that a square circle is a contradiction in terms. Has that it's a contradiction in terms kind of at the ends, because if you imagine like a rod or bar that's a circle on one side and the square on the other, then you can imagine kind of the way each vent or flute of it makes it so that it's a continuous transition of the least possible deviation along the way. Is for something that is just talking about, say, Nelson Goodman's account of green versus blue and grew, because that's the riddle of induction, and it just means that quasi-modal logic fails eventually, and so we have a modal temporal relevance logic to keep that square. So the outer products, again, make it so to keep Aristotle from being made a fool, and Hegel from being trapped in a lie. So the book addresses questions of the definitions of mechanics and the unmoved mover and the immovable object and the unstoppable force, and then about things about definition, the cycles, creation and destruction, conservation, the ship of Theseus paradox. That this book reflects a well-informed coverage of many of the ideas involved with the first cause and final principles. Again, totally apparent matters of the tradition of making for the principle of sufficient reason there for first cause and final principles, about though why scientism's arrival, that scientism itself is that, and then it's empirical, and it doesn't say anything while saying everything at all, is that, then has it so that it makes for a broader account that, again, this author might have been just kind of like stuck with, because he would have to turn over the entire canon and dogma and doctrine, and then what arrived in the 20th century is that the abandonment of causality for easy to pick up and put down little theories, that to be talking about foundations in a great theory instead of just like this works on any small theory you want to figure out, has that it comes back, the notions of the first cause or first principles and final cause. If this was about an eternal first cause, is like the demiurge or unmoved mover. That is Aristotle put it, circular movement is eternal. Infinite density, galaxies and their spiral shape, dark energy. Whatever happened to Occam's razor? It seems like modern theoretical physicists do not follow that principle at all anymore. There's Schaffer's lasers. If Occam's razors do not multiply ideas unnecessarily, meaning eliminate what's not so, and then what's left should be so. And then there's also, it's like, well, you can't dumb it down too much. Don't multiply fundamental entities unnecessarily, for the notion of Schaffer's laser. But at the same time, it's like, don't multiply contrived epicycles unnecessarily, because sometimes it'd be a simpler account to just say it's like so in a case, but then in all the cases it would make an explosion of the cases. Then that's not actually applying Occam's simpliciter or necessitam or suppositios. suppositiones, to make for an account of why the paucity of resources, the efficiency of things, is according to the KISS, keep it simple and stupid principle, as that being efficient and fair and not overcomplicated when giving an account of why something could be so. Still can't be too simple, or else that would fail. And so in these sorts of accounts, that gets into why then when discovering the idea of theoretical physicists in Occam's razor, yeah, you can find examples either way that are wrong, but then the idea is to find ones that both ways are right, and that two wrongs do not make a right. It's talking about infinitesimals and infinity, and the indefiniteness. It's like it can't be defined, because then everything off it could be derived. So the inconsistent multiplicities here make for instead indefinite forms, indeterminate forms, that then have real analytical character according to the considerations of their conditions. Talks about Nietzsche and a way to take something from Nietzsche that would make a fallacy or otherwise that is just a great source of being able to break otherwise the inconclusive, not sufficiently thorough reason. Gives some accounts of the syllogisms, or like these are linear derivations. So this would be like so contradiction. This would be like so contradiction. This would be like so contradiction. Whatever is given first kind of makes it last wins. And so when you have C rule 1 is like the inductive source of truth, and then the idea for making any kind of proof by contradiction is like, well, there was contradiction, so whatever was first can't be so. Then to put those together, it makes for why that proofs by contradiction are generally considered not part of constructivist mathematics. And then furthermore, that the syllogism is to be read every possible number of ways, because for the relevance of them to each other, because otherwise it's assigning a relevance just to the order in which they're stated. And so it's not so much that Aristotle can't read, because he reads everything every possible way. And then the notion that then, as a matter of being fair, and according to Grice, polite in communications, it's given as a linear narrative with the implicit idea that it's like these are given in an order, the statements. I don't know if they would be in an order, that the way that thusly syllogism will keep it that Aristotle is not made a fool, has that they have to be constructive in the sense of monotonic. They can't affect each other unless they're particularly relevant in these terms. That quasi-modal logic with its irrelevance of terms, false consequent or false antecedent, saying anything at all, is one of the great tragedies of modern accounts of logic. And that our classical modern logic is after Chrysippus's moods, because Chrysippus, hundreds of years before Neo-Stoic and Neo-Platonists made for Neo-Hegelian, Neo-Kantians, these half-truths and lies about otherwise the truths of these matters, makes for so that this way, thusly, these accounts where the author can readily demonstrate inductive impasses, still has then for the greater resolution that there's the meeting in the middle, these analytical bridges, then about those being particularly mathematical, about the geometric series, line drawing, the iota-values, and the spiral space-filling curve of an axiomless geometry, point in space. Talking about cosmology, the Big Bang Theory. If the amount of possible worlds was finite, then the time that it would take to find that world would also be finite. More about Nietzsche. Al-Kindi in questions of the finite, regression, ad absurdum. Not the ad infinitum, which is somehow precise and completes things instead of going off to all the explosion combinations. He says Aristotle considered the past sequence of events to be a potential infinite only. Aristotle had these other constructive accounts. You have to kind of read Aristotle more thoroughly if you're not going to be left half adrift in a world of inductive impasses, because then you'd just be blocked by the fact that induction claims to complete itself, and as a rule, it's a trustworthy rule. It will never go wrong, but the problem is that sometimes where it's going is already defined by something else, and then it just doesn't know that it's wrong. It's the invincible ignorance of inductive inference. Besides its strengths, acknowledging its the greater strength of what can be also made as inductive accounts, but deductive accounts more thoroughly. The cardinality and ordinality of infinite sets. Here it mentions Burali-Forti's antinomy, or paradox. So Burali-Forti is to ordinals what Cantor is to sets, cardinals. So Burali-Forti is a guy, and he's got kind of a joint name, Borali-Forti, Burali-Forti. And so he says, hey, the way we're making ordinals has that if you take a set of those, then that would also be an ordinal, and it would be infinity, and it would be the universal ordinals. And its name is ord, the ordered type of all ordinals, or just their set as ordinals when it composes that way. So it's the ordinary, and then it would be an infinity that contains itself, because then it would also contain itself. So Burali-Forti's paradox is resolved by it's like there must be the extraordinary. And then we only have analytical bridges, and then to keep set theory from being broken about the uncountable, so it's like, well, at least one of these functions, another thing it's defining in set theory, it's like define numbers in set theory, define geometry in set theory, define ordinals in set theory, define all matters of mathematical objects by their various different theories in set theory, because it is a theory of one relation, so it's fundamental that way, makes for the reasoning then why for functions relating things for the cardinals, that those bijective functions define what cardinals are by the equivalence classes of sets that have functions one-to-one and onto between them, has that, then it's just as simple to say, well, then to make our analytical bridge, because we have these analytical bridges to solve the inductive impasses and keep from going into the chasm of inductive failure. The analytical bridges here is make for, well, now we've also just demonstrated that not all functions are Cartesian. And so instead of the usual account, it's like, well, given a function, I can compose it with any other function with a compatible domain and range. They make a function. Functions compose. It's like, well, that's simple. That's because the whole space of all their possible values in the domain and range, all the possible combinations, the power set, if you will, of those, on either side of the domain and range make for that all functions, according to that definition, are Cartesian in this ordinary theory. And it's simple enough so there's a special one where it doesn't. And so then that keeps a countable continuous domain like line reals from being contradictory or contradicting both ways. The usual account of the complete order field. And then it also makes for the account of Burali-Forti and the power set result of uncountability, that the set of all sets that don't contain themselves would, that be as along the lines of Russell's paradox, then has for the power set result where it's taken the element that's missing, as for the set of all sets that don't contain themselves, has that, it reduces back to Peano's function of the successor and order type. So these ubiquitous ordinals saying is like, well, the only way that talking about ordinals in a set theory is not going to be contradictory is to exemplify set theory in a model of ordinals as well. So these two theories of one relation basically result meeting for each other in the middle, that these ubiquitous ordinals make for a Peano's successor, that the successor is the order type, is the power set. And so that then this leads extraordinary, the ordinals theory, to have that is like, well, one defines equal size, the other defines different size. that's just as a way to make it so simple then that there's an account then modeling them in terms of each other, that the analytical bridge can be constructed from these ponts, these bridge points on either side. So that's a way to keep mathematics and mathematical foundations true to its name. Epigrammatic, eponymous. Vis-a-vis, I'm pleased to read from this author that like, hey, have you heard of Burali-Forti's paradox? It's like, yeah, anybody who studies set theory and trying to figure it out, and especially why the line reals exist, would have heard of Burali-Forti's paradox, and that it otherwise makes for an account of at best incompleteness, and then is about independence of number theory and accounts of laws of large numbers according to foundations of mathematics, and the usual account, and equi-interpretable with proof theory, the model theory. So that's great. Giordano Bruno, he talked about, like multiple on the plurality of worlds, like there's more in the universe than just Earth and us Earthlings on it, thinking and feeling beings of a sort. And then about things about infinity. Let's see what he says. If there's anything about that, there would be infinitely many of those. Is kind of what is arrived at. But then about points and endpoints and midpoint theorem and this kind of stuff is then for Brentano and boundaries, because going back again to the idea of like, well, is a point, does it have sides or not? It's like, well, in a sense it does, because if it's a boundary, a point on a line or in a line, it kind of is. And here there's a distinction made between points in a line, like these line reals, and points on a line, somehow found on the field reals. And then there's points as of about a line for the signal reals. 3 kinds of continuous domains for 3 laws of large numbers, 3 natural infinities, 3 natural continuities, 3 models of Cantor space. And then as with regards to class set distinction and set theory and ordering theory, with regards to sets and ordinals, usual simplest accounts of mathematical objects from theories of one relation. So this is a nice pamphlet of accounts. And then getting into like Hilbert's account of infinity, it's like, well, have you heard of Galileo's account of the equivalency of countable infinite sets? It's like, no. It's like, let me tell you, it's kind of like Hilbert's hotel. It's like a bunch of numbered things, and there's something in them, and rooms, and then there's infinitely many of them. Let's talk about that. And it's like, oh, well, and then that makes for Dirichlet and the pigeonhole or cubbyhole principle. It's like, well, I got these between the other. Is there space in between them? Yes or no? So that's about the integral moduli and these sorts of accounts usually. The Dirichlet principle, which is applied in mathematics, is like that is a step in so many proofs of mathematics that it doesn't really attain to then the greater account of Dirichlet problem, which is like that in the infinite and these sorts of accounts, and the necessary the bookkeeping and the matters of rates and relation in rates of the things, the bookkeeping. So that then is for measure theory mostly, usually, always, Dirichlet problem. And then for Poincare completion, that being an account of Dirichlet and Poincare were kind of contemporaries, and Dirichlet made a great account of the Fourier style analysis and made it a thing. And then Poincare gives for the cetus, analysis cetus, S-I-T-U-S, the analysis cetus, space inversion, and again accounts of the higher geometry, as Graustein put it, for what became algebraic geometry in the 20th century, and the various accounts in algebraic geometry of candidates for foundations or frameworks, as they usually are. They can't quite be foundations proper. They can still kind of be a framework of things. And indeed, they won't be swept. It won't be for sweeping under the rug. These things when they're put down, they're still examples of not perfect theories. The author ends with he says he disagrees with Russell. And if we assume, and the thing is, usually the matters of idealism is that we don't assume anything. It's axiomless. Axioms are assumptions. And it makes for a logicist and a positivist account, but there already is one. There's a natural one. And then we just have to attain to that. So anyways, this is a great little book, and I'm glad I've had a chance to look through it. And it's for somebody who's curious and interested in things, and then to offer some of the terms and the relevance of things. And it seems well enough written. And then it points to some of the antinomies instead of paradoxes or whatever. But then that's about what there is to it. So anyways, that's about today's reading foundations, a paleoclassical postmodern account, where infinity and continuity are real, natural, central, primary. And that's mathematics.